The ship is already moving before you even see it. A fully loaded container vessel, 300 meters of steel and cargo, is threading a harbor channel at dead slow ahead. Near the stern, a row of windows catches the morning light. That is the bridge. That is where the captain is standing right now, looking forward across the entire length of the vessel at the narrow gap of water ahead. And if you have never questioned that before, you should. Because on every car, every bus, every train, every piece of machinery humans have ever built to move from one place to another, the controls sit at the front. The driver watches the road from as close to the leading edge as possible. On a ship, the controls are at the back, as far from the bow as the designers could place them. And that is not an accident. It is not a tradition nobody got around to changing. It is the only answer to a physics problem so extreme it rewrites everything you think you know about how large moving objects are controlled. Here is where it starts. We sit at the front of everything we drive for one reason. We need to see what we are about to hit so we can stop before we reach it. At motorway speed, a car needs roughly 70 to 90 meters to stop in an emergency. A loaded bus needs more. A freight train needs significantly more again. A fully loaded supertanker traveling at normal sea speed needs up to 8 kilometers to stop. 8 kilometers. That is the length of about 80 full-size football pitches placed end to end. From the moment the engines are thrown into full reverse to the moment that ship comes to rest, you could drive across an entire city. The ship does not slow quickly. It simply continues, vast and indifferent, bleeding speed across kilometers of open water. At cruising speed, a fully laden supertanker carries kinetic energy roughly comparable to the detonation of several hundred tons of TNT. You are not steering around problems at sea. You are spotting them far enough in advance that a gentle correction now means you never make an emergency one later. The ocean is not a road. It is a chessboard where every move is calculated several turns ahead. This changes everything about how you think about ship design. On land, control means reacting. On a vessel of this scale, reacting is already too late. The entire geometry of command is built around seeing what is coming with enough time to make a decision that will not take effect for several minutes. Speed and mass have removed sudden response as an option. The only viable option left is anticipation. So the view forward matters enormously. And this is exactly where bridge placement begins to make sense. A modern container ship is roughly 300 to 400 meters long. If you place the bridge at the very front, directly above the bow, you would have an unobstructed view of the water ahead. That sounds like the obvious answer. But you would have zero view of the ship behind you. You would be standing at the tip of a structure longer than the Eiffel Tower is tall, unable to see what the remaining 300 meters were doing. That matters far more than most people realize. A ship is not a rigid arrow pointing at a destination. It is a floating platform with a hull that responds to cross currents, a propeller pushing from the rear, and a rudder that steers by redirecting that thrust. The front of the ship goes where the back tells it to go. The bow is the passenger. The stern is the driver. Every correction originates at the rear and travels forward as a consequence. Standing on the bridge of a fully laden container ship is like standing on the roof of a 30-story building, sliding sideways through water at walking pace, while tugboats push it from multiple directions below. Everything that matters operationally is happening behind and beneath you. The bridge at the stern puts the captain directly above the point where the most critical action occurs. Not the bow, not the middle, the stern. Here is the part that breaks common sense entirely. Moving the bridge forward would actually make the ship harder to control, not easier. The reason almost nobody outside professional maritime work understands this is that they have never watched a large ship actually berth. They picture it like parking a car. Line up the front, ease gently in. But docking a container ship is nothing like that. It is closer to parallel parking a building using only mirrors in a crosswind with the stopping ability of a glacier. When a container vessel makes its final approach to a berth, the maneuver is controlled almost entirely by watching the stern quarter. That is the rear corner of the hull, the point physically closest to the dock, the point that, if it swings even slightly too far, will make contact with a concrete pier at the combined weight of 200,000 tons, moving at what appears to be a gentle crawl. It does not look violent. The consequences are. The captain, and often the harbor pilot who boards the vessel for the final approach, stands on the bridge wing. That is the open platform extending out from the side of the enclosed bridge. They lean over the railing and look straight down. They are reading centimeters, the narrowing gap between hull and dock face, the angle at which the stern quarter is swinging, the rate at which that gap is closing. If the bridge were positioned at the BOW, that view would be completely impossible. The captain would be standing 300 meters from the critical zone, staring at open water, trying to estimate the geometry of a maneuver happening entirely behind them, relaying instructions backward by radio, guessing at angles they cannot directly see. At the stern, they are positioned directly above the problem. The view is immediate. The spatial feedback is real-time. The correction happens at the source. This is not a marginal advantage. It is the operational difference between a controlled docking and a vessel that silently demolishes a port facility at 2 knots. Now add what is happening across the deck. A working container ship on final approach has crew moving along the full length of the vessel. Mooring lines are being walked forward by hand toward dock bollards hundreds of meters ahead. Deck officers are coordinating with tugboat crews over radio. In adverse weather, spray sweeps the deck in heavy sheets. From the stern bridge, the captain sees all of it in a single visual sweep. Every crew member on deck, every line running toward the bow, 300 meters of active working vessel laid out directly in front of them, like a map they are standing inside. A forward bridge makes that same 300 meters of working deck a complete blind spot. The captain stares at open water while everything operationally critical unfolds behind them. There is also the mechanical reality of where the engine lives. On almost every large commercial vessel ever built, the main engine is at the stern. On the largest container ships today, it stands roughly 13 meters tall and weighs over 2,000 tons. That is heavier than 350 adult African elephants consolidated into a single block of steel. The engine sits at the stern because the propeller shaft needs to be short and direct. Running a drive shaft the full length of a 400-meter ship would introduce catastrophic friction and power loss. So the engine is at the back, the propeller is at the back, and the mechanical core of the vessel is concentrated entirely at the rear. The bridge sits directly above this engine casing. The captain, navigation equipment, communication systems, engine controls, and officer quarters are all within one compact vertical structure at the stern. The captain does not walk the length of 2 football pitches to adjust engine speed. They stand at the console, and the engine room is directly below. That integration is the reason a crew of 20 to 30 people can operate a vessel that, by any other logic, has no business being managed by so few. Container ships grew steadily through the 20th century, then grew dramatically. Today, the largest vessels carry over 23,000 standard containers, stacked 9 high above the deck. When cargo occupies the entire length of the ship, there is no physical space for a bridge anywhere other than the very rear. The cargo claimed the deck. The bridge moved permanently aft. Earlier designs tried midships bridge placement, gaining partial sightlines both forward and aft. On shorter vessels, it was a genuine compromise. But as ships lengthened, midships positioning pushed officers away from the engine room and degraded the stern sightlines essential for docking. The stern won not through a single design decision, but through the accumulated pressure of real operations across decades. Harbor pilots feel this most directly. A harbor pilot boards arriving vessels by climbing a rope ladder from a small launch in the outer anchorage, then assumes command for the transit into the berth. They know a specific port with an intimacy no visiting captain can match. They know the tidal behavior at each bend, the exact moment to order engines astern, and the current patterns that push a hull sideways at low water. On a vessel with a properly positioned stern bridge, a harbor pilot steps onto the bridge wing and immediately reads the geometry of the approach. The dock is below and slightly ahead. The stern quarter is visible. The bow extends in a long, readable line forward. The picture assembles instantly for a professional who boards a different ship almost every working day. A forward bridge would force that same professional to mentally reconstruct the position of the stern from 300 meters away on an unfamiliar vessel in a narrow channel with the tide running. It adds enormous cognitive load to a job at the edge of spatial judgment. What you are looking at when you see that bridge at the back of a container ship is not aesthetics. It is not tradition. It is a problem solved completely and expressed permanently in the architecture of every large vessel on every ocean in the world today. The view forward covers the distances that the speed demands. The view downward covers the margins that docking requires. The deck is visible end to end. The engine sits directly below. The operational core of the ship is unified into one structure at the stern. The person making the most consequential maneuver of the entire voyage has the exact sight lines they need at the exact moment they need them. The bridge is at the back because the physics of the job demanded it. Every alternative was simpler to build, but none of them worked as well. Here is what follows from everything you now understand. The harbor pilot climbs the side of the ship on a rope ladder, sometimes in heavy swell, sometimes before dawn, and legally assumes command from the captain for the final approach. That pilot cannot be overruled. A stranger steps onto that stern bridge and takes the controls of a ship that crossed an ocean from the officer who sailed it there. The captain stands aside. Why that system exists, and why experienced captains welcome handing over the wheel at the moment of highest risk, is a story about port hydrodynamics, individual harbor entrances, and a kind of knowledge that cannot be learned from any chart ever drawn. If this is the kind of engineering reality that permanently changes how you see the world, subscribing means the next time you watch a ship move, you will understand exactly what you are looking at.